just want to announce again that there are just 3 remaining lectures today on Thursday and next Tuesday. So because next Thursday is Thanksgiving, and then the week after is the Harris conference, and then I'm gone. So finally we will have to talk about the real things. So space of Stukas. So I guess today's aim will be to describe the modular problem and compare it with the modular problem of p-divisible groups in the simplest case. So these modular problems are associated with the following data, which I will describe them more precisely. So the first datum is just the datum of a reductive group of a QP. And actually, it is interesting, very interesting to compare reductive groups. But that we're strict to the case that G is just in GLR. Now maybe at some point I will say something for a general reductive group, but whenever it becomes easier, I go to GLN. The second datum is that of a sigma conjugacy class, an element in what Kottwitz calls B of G. I will recall that in a second. And the third datum are certain conjugacy classes of co-characters. It's called the conjugacy class of mu bar, so they are sets of conjugacy classes. Many of them possibly. Conjugacy classes of co-characters. Okay, so let me start with a reminder on the set B of G. So that stuff is due to Kottwitz, and so I'm describing here the local theory, but Kottwitz has actually, I think earlier this year, put up a very interesting preprint on arXiv where he defines B of G for any local or global field. But in the case of a local field, it has a very concrete incarnation. So for this, let me take K, any algebraically closed field of characteristic P. It could be F3 bar, but it could be anything. And so L will be this string of bit vectors invert P. And so the absolute for B is x on K, and so it x on L. So I get sigma here. Here. And then you get an action of the group, the LYU point of the group, on itself via what's called a sigma conjugation. So an element H in G of L, X on G of L by a sigma conjugation, which is G is mapped to H inverse times G times sigma of H. And I guess a basic theorem due to Cockpits in this situation is that B of G, defined to be the sigma conjugacy classes in G of L, is independent of K. Let's try to understand what happens here in the simplest case again. So if G is this general linear group, rank R, then one way to think about sigma conjugacy classes in GLRL is that this is the same thing as a rational Dieudonné module of rank R, of dimension R. And it's R-dimensional L vector space. And phi is a sigma linear isomorphism. Just by sending an element G in here to the free guy with phi being G times sigma. And so if you change the basis of this Dieudonné module, then G is precisely changed by sigma conjugation. And this letter set by Dieudonné-Manin, which classifies such guys for an algebraically closed field, are just given by their slopes. And so one way to write down their slopes is as a decreasing sequence of rational numbers, so lambda I and Q. And they need to satisfy some integrality condition, which says that for all lambda and Q, lambda times the number of i's for which lambda I is equal to lambda has to be an integer. So that's just an awkward way of saying that any such Dieudonné module is a direct sum of such simple guys corresponding to rational numbers. Whereas the guy of rational numbers has rank R, and so if you have something, if you have such a simple guy, you need to put that slope as many times, which gives you this integrality condition. And so
so it should depend on R in some way?
Yes. I made the same mistake as yesterday. I was calling this n and this n the same. And so in this case, one also calls lambda 1 through lambda r, which you can regard as canonically as an element of the co-character group of GLR. The rational co-character group, and it's dominant in there, just let's say decreasing, and so that's known as a Newton point. Of the sigma conjugacy class. And so in this case of GLR, we see that the Newton point actually determines the sigma conjugacy class. That's not always true. So in general, there's some other invariant known as the Kottwitz invariant, and the two together determine the sigma conjugacy class. So let me call this part. So in general, have the Newton map, which I think is called nu for Newton, which goes from B of G to co-characters of G, rational co-characters dominant. And another guy known as kappa, which goes from B of G to the fundamental group of G over QP bar, take co-invariants under the inertia. So this pi 1 is Bauer-Weiss pi 1, which is not pro-finite. So for an algebraic group, you actually have a pi 1, which is a finitely generated abelian group. And this gadget here is the inertia.
Sorry, when you say in general, you mean georeductive group?
Isn't that right?
Like if G is anisotropic, then there are no, what does X star G mean? Geometric co-characters?
I was base changing my G to QP bar here.
No, the line above, sorry.
The line above. If G is anisotropic, then I
think you take rational character.
Oh, anyway, it's just a map. So.
I think that's still right. I think then in this case all sigma conjugacy classes should be basic, and yeah, I think it's okay. It's stated.
Sorry, G is defined over which field?
G is over QP.
Over QP.
So here.
And you really take co-invariant under inertia and not the full Galois group?
I really take co-invariant under inertia, yes, that's because it's an element of G of L. Sorry, I'm confused. Like, are you sure? If you're sure, then I'm fine. I'm like
That's what I'm used to.
Okay, yeah, then hang on. Sorry. Sorry. Yeah. So, I guess one way to think about this this second map, known as the Kottwitz invariant, is that in the equal character case, you can think of the map which goes from long series valued points of G to pi 1 of G covariance under gamma as a map which takes an algebraic loop and maps it to a topological loop.
Sorry, what is the statement about these two maps?
So the state, sorry, yeah. So then, if you take them together, lambda kappa, that's an injection from B of G into the product. Times it's an injection, and you can describe the image. So one thing you have is that like the two elements maps to something comparable, namely just probably
lambda is new.
Sorry. Yeah. So for GLN, for example, this element in here that you're getting is just kappa of some G is just the so you take the p-adic valuation as a determinant of G, which is an element in the integers, which is pi1 of GLR. And this can be read off from the Newton point. So in general, this kappa just adds some torsion information. So kappa as an element of this group tensor Q is determined by the Newton point. So I need to say something about the relationship between d of G and vector bundles on the Fargues-Fontaine curve, or such things. About which Farg will probably say much more during the Harris conference. So for this, let me consider let R plus be any perfectoid K algebra. Yes. And so then we get in EB with a phi over the following space, and I will say how it's constructed in a second. So it was the p-adic spectrum of R plus, removes the loci where either P or pi is 0, where as usual pi and R plus is a pseudo-uniformizer. Over space. As EB, so I should just take a sigma conjugacy class for GLR. But okay, so this B corresponds under this dictionary there to a Dieudonné module n phi, up to isomorphism maybe. And so you just take the structure sheaf of this guy and tensoring it with this Dieudonné module. And so here you have phi tensor phi acting. And so this gives you the phi EB. Let me also recall what my notation is here for this y. So that's supposed to be just a y0 infinity for R plus. So what's the general picture here? So I guess my point was just a geometric point, and this is what I've previously denoted by this way, y0 infinity. Just follow this. So for any R plus, one can consider this a space Y for R plus. So to make it compatible with the notation for a geometric point, let's say it's a complement of the locus where both pi and war pi are 0. And so this still comes with a map which I also called kappa, unfortunately. To the topological space 0, infinity. So the picture was, you have here's a locus p equal to 0, this locus pi equal to 0. We're removing that part, and then we have some space living over here. And this has a map to 0 infinity, which measures the absolute value of pi versus the absolute value of pi flat. It's like it's a logarithm of 1 with respect to the base given by the other. And then what? Then this y open bracket 0 infinity is just the inverse image of 0 infinity, and I also have something which includes the p equal to 0 part.
So on underlying sets, this kappa map you're kind of using like for any point you have this kind of associated rank 1 point and sort of
Yes.
Why are you removing both axes here? In the definition of the...
No, I'm not removing the x's.
No.
In that definition. So I always have to move the x's where pi flat is 0 because I'm really, so I suppose it to the R plus, and so an R pi is invertible. But I need to remove p equal to 0 because my n just starts life with a qp. Yeah. So that's something rational, so I have to remove the locus where p is equal to 0. And so, a theorem of Fargues-Fontaine in the case of the general linear group, and then of Fargue for all G, is that if I'm doing this in the case of a geometric point, C it's algebraically closed, not like a median field. Then this gives a bijection between V of G and, in a suitable sense, defined G bundles over the Fargue-Fontaine curve, which is the same thing. So this was just this y0 infinity modulo force of Frobenius, and so that's the same thing as to say phi equivariant G bundles. Up to isomorphism, of course. Well, Fargue also tells you what exactly a G bundle is, but like all reasonable definitions should be the same.
Like the étale topology versus whatever.
Is Fargue here? Sorry.
No, he's in Boston.
So he's more speaking there about the theorem just now.
Yeah.
Yeah, right. So you might either define them as an actual G torsors, or you might define them using some Tannakian formalism, or like I think all of these things that turn out to be the same.
And the fact that you get the same answer on the scheme or the adic space, that just reduces the GLR case?
Yes, that you use, for example, you use the Tannakian business to the GLR case. Yeah. Okay, so G bundles on that curve are still classified by the same B of G. Okay. So this will be used in the following in the. So I'm interested really in some modular spaces of Stukas, and so if I have any phi e. So Stukas, I recall, live over the space y0 infinity where I don't remove the part where p is equal to 0. So this is any Stuka. Then near infinity, i.e. over y r infinity r plus, where r is very large, or actually somehow the complement of any quasi-compact subset. Any reasonable definition of near infinity is the same thing. This phi e is an isomorphism just because it has only finitely many poles or zeros. And so then such phi modules over just yr infinities are extend uniquely to the whole thing, y open bracket 0 infinity. And so if R plus is COC is a geometric point, then there is a unique B and B of G such that E phi E restricted to y r infinity is isomorphic to EB phi EB y r infinity. And so, to get a good modular problem, you should somehow fix what this is near infinity. So. I.e., you need to fix the sigma conjugacy class B and B of G. Okay. So that explains the role of the B. And so next, let's consider the co-characters. So such co-characters are conjugacy classes of co-characters classified by co-characters of T mod Y group, where T in GQP bar is an decimal torus. Yes. And so you can always represent, there's a unique dominant representative always, if you also fix a Borel. And so if G is GLR, this is given by a decreasing sequence of integers. KI1, KIR. So in that case, there's also no difference between like what happens over QP and what happens over QP bar. As the group is split. And so, I should also say that there is now a dominance order. On the possible mu bars, possible such conjugacy classes, and let me just explain what this means for GLN. It's a modularization order. So a sequence K1 up to KR is considered to be greater or equal to the modularization order in K1 prime to KR prime, if and only if K1 is at least K1 prime, K1 plus K2 is at least K1 prime plus K2 prime, and so on. And the total sums are the same. Okay, so, and so I should also say that I let EI be the field of definition, so that's containing QP bar, be the field of definition of this conjugacy class. Sorry. So the set of all characters in the conjugacy class forms an algebraic variety. Field of definition of that guy. Good. And so
is that field finite over QP?
That's finite over QP. Yeah. And so I think now I can try to define this modular problem of Stuka's. So and so let's say we represent B by some element G in GL, GF, L, where L is what I will denote by QP breve in the following, which is the vectors of FP bar. Can always represent this over FP bar already. It also doesn't really matter, it could also choose a bigger guy. And that EI breve be the compositum of EI and QP breve. Where you probably regard this FP bar there as the residue field of this chosen QP bar that's around. And so we are trying to define this space with Stukas, GB, and then we have these μi bars for I running
So
through.
does the fact that, as you were saying before, that these things are independent of the field, so like in this case here you can really find that representative, does that somehow use this theorem that G is always at least quasi-split over this L or something?
It probably does. Well, I shouldn't say anything because it.
Okay.
And so this is supposed to live over this bar D, E1 Brev, and it takes a fiber product, let K be a bar. Over K of all these bar Ds. Nice. Sorry. I guess my definition is only for. Sorry. Let me say the following. So in general, so some of my notes are not very inconsistent with whether I really just consider G or GLN, and so in general, let me just say that in general we should have this modular problem over that space there. And maybe I should also somehow introduce some K where K is in G of QP is a compact open subgroup. But if my group is GLN, then I somehow have GLRZP as a canonical compact open subgroup in there. And then also all these EI graphs, they are just QP graphs because all these conjugacy classes, they are already defined over QP, and so something simplified. So this implies. And so, okay, so let me just define it in this case. GLRB bias over so what are the test objects? The test objects are perfectoid guys RR plus, which come with n many different maps to Spadi QP graph, but they're supposed to give compatible K structures. So I can as well regard this K structure as somehow being part of the data. Taking a perfectoid K algebra RR plus with n maps maps over K. So
P bar?
Yeah, K is still F bar.
Oh, sorry.
So these n maps, they correspond to n untils Ri sharp over QP. I running from 1 to n. Cubic red. Two. E phi E, a Stuka of rank R over this Y 0 infinity R plus. I mean, that's what I like. Stuka's by definition are guys over that space. With pause only at the xi, which I recall, so these untils can be seen as maps from the adic spectrum Ri sharp plus, sitting inside this y0 infinity R plus. These pores are supposed to be bounded by mu I bar in a sense which I'll explain in a second. And an isomorphism between this guy and this fixed EB phi EB over R infinity for any sufficiently large R. No. In such
RR plus thing, right?
yes. So I suppose I have to explain what I mean by this. So and so so that is a condition which I impose at all geometric points of rank 1, that's enough. And so there's a relative position of, so my interpole, you have two different lattices in the same Biederaum vector space. So the relative position of the image under E of phi E upper star restricted to the completed at X and E itself completed at X are two finite, so free rank R Biederaum plus of CI sharp modules with the same generic fiber.
that on the left one is the restriction is inside the phi e? Does that make sense?
I see.
Oh, okay. Yeah. No,
Doesn't make sense.
no, yeah.
Uh,
Yeah.
well, I guess it would be. Yeah, I think it's fine. Like if I would put it inside, I would have to restrict to phi inverse of xi or something. Yeah. So their relative position is given by a sequence of integers. Let's call it just k. K1 at xi. Kn at xi. Kr. And so the requirement we have to make is that then this K1 at xi so I would like to say that the requirement is that it's less or equal to the modularization order to the thing which corresponded to mu I bar. But actually that's only true as long as the points stay distinct. So, and so in general it might be that several of the points collide, in which case you should sum up the corresponding guys. So what I should actually be doing is I'm summing up over all the j such that xj is equal to xi. I sum these up. And this sum is really just a termwise sum.
Why not just add up everything? A single upper bound and everything. Oh, you really want this? Okay.
Yeah. No, I mean also I want my modular space to be proper eventually. So the thing with the modularization order is that this some of this relative position of cadetness, it only goes down under the modularization order in the specialization. If I have 2 points collide, then I have to sum up the corresponding relative positions. And so to get something which has a chance of being proper, I think you have to do exactly that.
And it will be a functor even though you...
Why should it not be a functor?
I mean, you're summing over the condition of equality.
I'm checking this just at geometric points. So geometric points.
Sorry.
Yeah. Otherwise, there's also not really a relative position. So I mean, only at geometric points is really a complete discretization, right? Yeah. So I think that's the correct way to make this precise, and I think with this precision, I think that's a precise functor.
You want this to be proper over the product of the SPD?
Yes, so in some sense it should be proper. Well, no, it should not be proper. So it should not be quasi-compact. Like it should be like a Rapoport-Zink space. So it should be partially proper. Well, there's several directions in which you might somehow go to infinity, and I don't want like the direction where you can somehow go smaller in the modularization order and such a thing. I want to keep all of this there.
And this construction is functorial in the triple GBUI?
This construction is functorial in the triple GBUI, yes. So I think one thing you can do, at least for a group which is reductive over ZP, so with a chosen reductive model, is you can replace everything somehow by G bundles here, say in the Tarnakian interpretation of the G bundle. So what I will try to do in the remainder of this lecture is explain the simplest case of this construction.
Is the general case built out of this directly, or you just make a fancier definition? General G, you just...
For which are not unverified.
Yeah.
So the issue is that if I have the Stuka really including this point at 0, I'm somehow already specifying some kind of level structure automatically. So you would have to tweak the definition a little bit with the level structures, but apart from that, it's okay. Yeah.
What is the role of the implicit GLNZT? There is an implicit GLNZT here, which...
Well, in that case, like G bundle is really just like a vector bundle, which makes it easier to say what I mean.
So, could you say what would be the definition in general?
And the other thing I was using is that like I have a specific model, reductive model over ZP already.
He means like for general capital K with GLR.
For GLR, that will become clearer after the discussion I'm about to give. So essentially, I'm trivializing the Stuka in infinitesimal neighborhoods of this point 0, or where p is equal to 0. So I guess what I want to explain is the relation to Rapoport-Zink spaces. And so that corresponds to the case where n is equal to 1, and this conjugacy class of co-characters is what's known as being minuscule, or slightly more precise. Like for GLN, there's probably some central twisting that would be allowed. So I really want this co-character to be of the form a few t's and a few 1's, where I've probably I never know what should be d and what should be n minus d, r minus d. So this corresponds to a sequence 1, 1, 0, 0. Whereas there are d many 1's and there are r minus d many 0's. Let me just state a basic fact, at least in this case. So in general, you should put some compatibility between the b and the mu i's. And at least in this case, it's true that if the space GLR B mu is non-empty, then this B has to lie in what's known as the GLR mu, as a mu admissible set. Stick with the basic classes, which just concretely means here that all slopes IB corresponds to some n phi, and this n phi actually comes from a p-divisible group, corresponds to x over fp bar, a p-divisible group. So meaning that all slopes between of this b are between 0 and 1, and it actually has to be of dimension d for some normalization of Dieudonné theory. Of dimension d and height r. Okay, so And then really this x again determines this co-character. So really the only datum we really have is this x now. In this simple case. So let me recall the Rapoport-Zink spaces. So let's take squared x, a fixed p-divisible group, so over P bar say, a p-divisible group of dimension d and height r. And then Rapoport-Zink proves the following representability theorem. So they consider the following modular problem. So the functor from formal schemes over spiff ZP brev, where ZP brev is just the ring of bit vectors of FP bar. Two sets, sending S to the set of p-divisible groups over S plus the quasi-isogeny rho between the reduction of this guy mod P and the constant guy. This part where S bar is just a base change to the special fiber. Isomorphism. This gadget is representable by formal scheme. Let's just call it X, which is formally locally of finite type. Actually, formally smooth also, but formally locally of finite type. Locally forms, all the way around. Meaning that it's locally isomorphic to this formal spectrum of CP brev, where you have some power series variables, T1 up to Tn, and some convergent power series. But it's not quasi-compact. But all irreducible components of the special fiber are proper.
Quasi-isogeny?
Quasi-isogeny? It's an element of Hom invert P. Which is invertible in that category. Well, locally it's an isomorphism.
Yeah.
Globally, the denominator might be very big. Good. Here I am.
And this localized, I mean, here you just meant locally it's this mod something.
Sorry.
I mean, it's not literally locally like that thing, right? Anyway, you're just trying to express what formally finite type means, right?
Well, formally locally of finite type would mean it's mod is ideal, but if it's formally smooth, can't you?
Well, who knows what the residue feels like?
Sorry. Yeah, sorry. Yeah. If I would allow some metal localization, then it would be some metal localization of that. Yeah. Yeah. So if it's locally formally of finite type, it means isomorphic to a quotient of this by some ideal. Good, thank you. Okay, so I guess the space of Stukas I was defining lived only over the generic fiber, and so that mx qp would be the generic fiber over the adic spectrum. And then the theorem is that if I take the associated diamonds, and this is really gives this space of Stukas. Do I need any more decorations? I think it's okay. So over this body.
Definition of Stukas, the space of Stukas cannot extend over to y when you include 0? So that you get something integral here?
It's a very good question. Can I recover the space over ZP level? Yes and no. So I think this functor continues to make sense even if the points xi go to the point p equal to 0.
Yeah.
And you can also. Well, the issue is that integrally it's not analytic, and so I haven't defined an associated diamond, but like up to this issue, yes. Although the proof I'm about to explain will only identify the generic fiber. Yeah, so if you look at it like to write down the modular problem, it's really not critical that these points are away from p equal to 0. It will only become critical if you try to impose level structure. Yeah, so for the same reason that in yesterday's talk I wasn't quite, formalism was not optimal, it's not optimal here either. And, yeah.
So what was yesterday's talk?
Yes, you can watch it online. Yeah, it's a conference. Let me give a sketch of the proof. So the proof will use period morphisms, which are defined on either side of this. So, for example, you have a period morphism from x over qp brev, like its generic fiber, to some Grassmannian of type dr. So, usual Grassmannian over qp bar, considered as an adic space. And I guess this guy has many names, so I guess first it came up when D is 1, and then it's probably called Gross-Hopkins. Then for general D, this was constructed by Rapoport-Zink. Sometimes it's also referred to as a Grothendieck-Messing period morphism, because it essentially comes from Grothendieck-Messing theory. And probably I will stick to Grothendieck-Messing. So how is this defined? So if you have some such x and rho, then the Lie algebra of the universal vector extension. So then I should start the other way around. So I have the Dieudonné module of my guy x, this fixed guy, and this lives over QP-Brel, and I can tensor to the structure sheaf of this guy. And then why is this quasi-isogeny rho in Grothendieck-Messing theory? This is identified with the Lie algebra of the universal vector extension of x. And the Lie algebra of the universal vector extension certainly surjects onto the Lie algebra of x itself. Invert P. And so on the left-hand side we have something free over ring R. And in writing this I probably implicitly chose a trivialization, or I really meant the Grassmannian of d-dimensional quotients of this vector space. And so this here is of rank D. It's a rank D quotient. And so from Grothendieck-Messing deformation theory, you can deduce that this map is an Ishal map of rigid spaces, and also two p-divisible groups which are sent to the same thing under this map will be quasi-isogynous. And so over its image, it parameterizes p-divisible groups inside one p-power isogeny class. And so that's equivalent to saying it parameterizes GLR ZP lattices in a GLR, well, sorry, it parameterizes ZP lattices in a P vector space of dimension R, or in a QP local system of rank R if you want. Okay, so these facts are proved in Fargues-Fontaine essentially, and now on the other side, we also have something called the Grothendieck-Messing period morphism, which goes from this modular space of Stukas to this Grassmannian. But now I have to, like, left-hand side is a diamond, so I have to regard the right-hand side as a diamond as well. So how do you define that one? So if we have E phi E some Stuka, which comes with an isomorphism, this has a port at some point x, plus an isomorphism between E phi E restricted to some YR infinity and the E corresponding to this sigma conjugacy class B. So I think the way things should work out is that probably it may be the case that I did some sign errors in my normalizations. So if I look at the inverse of phi e, then this is now a map in this direction, and this should be should be is a well-defined map. Only its inverse has poles. Such that the co-kernel, that's what's in the next line, of the map from E completed at X to phi upper star E completed at sorry, the map goes from E at phi of X to the completion of this guy at X is killed by the maximal ideal at this point, so by the kernel of WR plus mapping y theta to R sharp plus, and free of rank D over the untilt. So what happened here? So this mu bar gave us a band on the relative position of these two lattices, and here it says that at any geometric point the relative position is such that there is a containment, and the at each geometric point the co-kernel is in a vector space over the residue field of this dimension, and this implies in the same global length.
Does this
Locally free. Sorry.
Does this construction generalize or only in the minuscule case?
Which construction?
This map, this IGM in this position.
This p-adic, it just goes to something more fancy, yes. It goes to this F1 I talked about yesterday.
Ah.
The speed 1 plus guy.
Sorry, so you're saying the fact that this is killed by that kernel is somehow a consequence of the condition on the geometric points?
Yes.
Is that related to certain stalks in the fields or something? Or what's
That should be so hard to see. Oops. And so let's choose our R as big as possible. And so somehow whatever we're somehow in the region where phi E is still an isomorphism, we can somehow extend this isomorphism. And so this way we can choose R such that maybe not the point X itself, because there is a pole at X, but the point phi of X.
now we have two R's for them.
Ah. Well. That's it. Phi of X lies at y are infinity. Then phi upper star E at X. I mean it's E at phi of X. So this is still identified with n tensor over cubic rel R sharp. And this way we get a quotient which is this co-kernel there. Co-kernel of the map from E. Sorry, I'm confused. No, this is a map from E at X, I guess. Yes. Of rank D of this intended. I.e. a point of this Grassmannian. And so we have these two different period morphisms. And so the next thing you have to talk about is the.
So in either case, this is a Grassmannian sign something. It's not the same thing. I mean, n is the same as the.
Yeah, it's actually the same. Yeah. So. Yeah. There will also be some other map. Like the isomorphism will be compatible with all those period maps. Let me first talk about what we have to analyze is the image of both of these period morphisms. So let's first do the Stuka case, because that one is actually easier.
So we're not proving yet anything about this second period map in terms of its properties. Just
We're
looking at its image.
We're not quite proving anything there yet. No.
Okay.
Let's first understand the image. So I guess if you're trying to understand the image, we have to deal with geometric points. I guess to completely understand the image, you have to deal with higher rank points, but it turns out that the higher rank point is in the image if and only if the rank 1 point is, and so there's no issue. So this map here is partially proper if you want. So what happens over a geometric point? So given a point of this Grassmannian, we get some, let's call this E prime, phi E prime, over y0 infinity, by modifying this bundle that we have near infinity anyway, so this EB phi EB adds those points x phi inverse of x and all its iterates using this quotient of n tensor cubic of C#. So in terms of this picture, so we have some vector bundle. So we are trying to construct something here. Or no, we are trying to construct it away from the both axes. And so we have something near infinity, or in the whole thing, and then we're modifying it at x phi inverse of x, phi minus 2 of x, and so on, at all of these points here. But to get a point in the modular space of Stukas, we have to extend this over 0. So, because we are doing some of the same modification in all the iterates, Frobenius will not be in isomorphism anywhere anymore at x, but at all the iterates it will be. So phi prime is an isomorphism away from x. So let's ask ourselves a question. When does the phi module over y0 infinity, or let's just take some small s, extend to 0, s small. So if you're restricting to now some small neighborhood of this point, so where's this map here? 0 infinity. And again in a small neighborhood here from 0 to s, phi will be an isomorphism. So we're getting something, the vector bundle was a phi linear isomorphism there. And we want to extend it to the whole thing. And so let's recall that for any s greater than 0, we have the following description, that phi modules over 0s are the same as sorry, I wanted to say something different. Are isomorphic to finite freezing P modules. That's something I proved in the course of the proof of Fargues' theorem. So if I take phi modules over y0s and tensor CPQP, there is now a map to trivial of phi modules over y0s. Because those guys are all trivial, which are, and this is a linear category, those are the same thing as trivial vector bundles on the Fargues-Fontaine curve, because we can again spread out this thing over 0 infinity and then take the quotient by phi. And that was something else I stated. The trivial vector bundles on the Fargues-Fontaine curve are equivalent to finite dimensional QP vector spaces. And so that here is an isomorphism. In other words, a vector bundle, a phi module over here extends if and only if it's trivial, in which case the datum of such an extension is the same thing as the lattice in a finite dimensional QP vector space. So, good. And so, thus we have a description of the image, namely that graphs D are typically admissible. These locus. Maybe a priori just a set of points of this guy where is this phi module over y0s? It's trivial. Constructed in that way there. And so this is the image of the period morphism on the space of Stukas by this discussion there. And so the main theorem we need to prove the theorem I stated is the theorem of Fargues-Fontaine that also if you look at the other period morphism from the space of Stukas to this guy is the admissible locus. And the hard part is surjectivity onto that part. So it's easy to see the factors, but
And so yet again, this is a calculation of geometric points.
yes, this is something about geometric points. And so this was reproved in my paper with Jared. And there, so the essential part of this is somehow an existence result for p-divisible groups. So there are enough p-divisible groups on the left-hand side to account for everything that's in the admissible locus. And so my paper with Weinstein is reproved using this classification of p-divisible groups over the ring of integers, I guess what's here C#, as such pairs of finite frequency p modules. And don't shade the trashing. Because conversely, if you are on the admissible locus and you have such a finite frequency p module, so from that picture there, and the filtration, so this modification business gives you also this filtration, and this gives you the required p-divisible group. And actually, this theorem on the image of the period morphism and this classification result for p-divisible groups are essentially equivalent. And so, another fact that's essentially explained in my paper also with Jared, but is mostly a consequence of the p-adic comparison isomorphisms for p-divisible group, is that there is a map from this modular space of p-divisible groups to the space of Stukas, compatible with the period maps. And now you're essentially done because they have the same image and the same fibers. And like using a small argument, they're the same. And I guess I'm out of time, so I don't have time to explain this. So they both map exactly onto the admissible locus, and over the admissible locus, both of them parameterize, like the fibers are GLR, QP modular ZP.
Is this comparison fact in this special case, is this kind of like nice to know, or from the viewpoint of the general theory, this is actually something that's going to be used? Like this is kind of just an instructive example, or?
Well, it depends on whether you're eventually interested in. Well, no, I mean, like, yeah, it's hard to.
You mean you can sort of forget about the
No, I'm just wondering.
I mean,
of course, it's very nice. I'm just wondering, like, is this like maybe this is?
Well, I mean, eventually, if you want to say something about Shimura varieties using this stuff, it's nice to know that some Shimura varieties are uniformized by the Rapoport-Zink spaces, and it's nice to know that they are the same. Although potentially, it could be the case that you can prove such uniformization theorem eventually for more general Shimura varieties without ever mentioning Rapoport-Zink spaces. But like that's probably like quite far in the future, and.
So to return to the question of what's the role of K, it would be a Stuka which is not
yes.
extending
So
to zero.
I guess what we're seeing here is that near zero, such Stuka is just given by finite frequency p modules, and you can also like trivialize parts of this, like an infinite level trivialize the whole finite frequency p module. Yeah. which is equivalent to trivializing this, like this phi module tensor to an infinitesimal neighborhood of the locus where p is equal to 0. And this makes sense, like without the mu's being minuscule or anything.
Do these parameterize more general kinds of modular spaces? Or
yeah, I don't know. I mean, I guess people are fantasizing about some modular spaces of motives, and like these probably should be some kind of p-adic incarnations of them, but
hypersurface polarized, right?
yeah, I don't know. I mean, like in this picture I'm explaining here, some Griffiths transversality plays in some sense no role. So like the space would be of the dimension as if there was no Griffiths transversality problem. Whereas like yeah, for modular space of motives we probably want this Griffiths transversality assumption. Or I don't know what you want to do, but certainly from any kind of modular space of motives, like locally there should be a map to these guys, or